Hello and welcome to today's lesson looking at an introduction to momentum. Now this lesson is for combined science students in the physics part of the course in the forces module. So in today's lesson what we're going to do is we're going to try and define and calculate momentum. So we're going to define what the quantity momentum is, calculate momentum from given information, and then apply this information to understand how momentum can be used accurately and reliably in different contexts. So like mentioned before, we're going to look at the following part of the specification. So this part of the specification is found in the forces topic of the AQA Combined Science course, but it's also in the AQA GCSE Separate Science Physics course as well. So it's in a common content. So, over 300 years ago, Isaac Newton put forward his ideas on how objects move, and he spent most of his life looking at how everyday objects interacted with each other and caused these objects to move. Now, we call these ideas the laws of motion, and we call them today Newton's laws of motion. And to this day, we can still predict the behavior of objects on the everyday scale of the universe using these laws of motion. So, for example, how rockets fly, how humans move, how cars travel, how the Earth orbits around the Sun. We can use Newton's laws of motion to give us an excellent understanding of this everyday motion in the universe. Now, just to clarify, Newton's laws of motion do not apply to motion inside an atom. Here we use something called quantum mechanics, which is what we would look at A-level physics. Now again, Newton's laws are not wrong, they're just incomplete. They don't work on the small scale of the universe. And again, unfortunately, Newton's laws of motion do not apply to motion inside very strong gravitational fields or speeds approaching the speed of light. So we had to come up with a new theory to replace this, the theory of relativity. So again, it's not because Newton's laws are wrong, they're just incomplete. They only work on everyday objects, not very fast objects. But we'll look at the equations of relativity in A-level physics. Now, basically, even the theory of relativity, it can be simplified into Newton's laws of weak gravity and slow speed. Now, in the modern day, Newton's laws of motion are commonly stated as the following. Newton's first law, the law of inertia. Objects stay at rest or move with a constant velocity unless acted upon by a resultant force. Newton's second law, the resultant force is equal to inertial mass times by acceleration. Basically, the resultant force and the acceleration it produces are directly proportional for a same mass. In Newton's third law, when two objects interact, they exert equal but opposite forces of the same type on each other. Now, Newton, when he wrote these laws down originally, didn't write them down in this form that we see in 2020. Rather, he wrote them in terms of a quantity which he invented, the quantity of momentum. Now, we're going to focus on what we mean by momentum. Now, you tend to see, what do we mean by the word momentum? So you might have heard in sentences that, for example, in sport, this team has momentum. I fell over due to my momentum. Now in sport, you tend to say a team has momentum if they win a lot of games in a row. So for example, if Sunderland won 6 games in a row, they would have a lot of momentum going into a football game. Now, in science, in physics, momentum is how difficult it is for an object to change its motion. So, if it is difficult for an object to change its motion, it has a high momentum, but if it's easy for an object to change its motion, it has a low momentum. So, for example, a running rugby player has a high momentum. For example, a moving bus or a truck has a high momentum because it's difficult to change the motion of that particular object. So, what qualities do you have to possess a high momentum? What makes these objects, such as buses and running rugby players, why does it make it difficult to change their motion? Well, it's because they will either have a high mass or a high velocity. These are the properties which give a high momentum. So the momentum of any object is dependent on two factors, the mass of the object and the velocity of the object. So we can express this in the form of an equation. Momentum is equal to the mass of the object times by the velocity. Now we measure the mass of an object in kilograms and the velocity of an object in meters per second. So you are expected to recall this equation and memorize this equation for your examinations. Now we can symbolize this equation with the symbols P equals m times by v. Now m is quite obviously mass, V is quite obviously velocity, but P is momentum. Now, momentum is given the symbol P as it's the first letter of the Latin translation of momentum, or the word that was originally used, impetus. Now, Newton realised in his laws of motion that a resultant force was needed to change the velocity of an object, but he also realised that the effect of the resultant force was dependent on the object's mass. So in the modern day, we simplify this to F equals ma. But Newton thought to himself that because the velocity and the mass both affect the resultant force required, it was a bit challenging for people to understand. So he simplified these terms of mass and velocity to combine them into one super quantity, one combined quantity, which he named momentum. So he decided to simplify the system and consider the products of mass and velocity the momentum of the object. So we can work out what the units of momentum are, because if we know momentum equals mass times by velocity, well, we can combine the units of mass, which is kilograms, with the units of velocity, meters per second, to give our units of momentum, kilogram meters per second. Now, that's just from combining, like we said before, the units of mass and velocity because they're being multiplied in the equation. And we can also express it as the following. So, we've got it as such like that. Now, in addition, if an object is not moving, it has no momentum. So momentum is a dynamic quantity. Every object which is in motion will have a non-zero momentum. So the only time an object will have a zero momentum is if it is stationary. Now that makes sense because the equation is momentum equals mass times velocity. So if velocity is equal to zero, any number times by zero will equal zero. Now, momentum is a vector quantity, which means it has both a magnitude, a number, and it has a direction in which it acts. Now, we can show the direction of momentum by the sign of the calculated values, positive and negative. So objects moving in opposite directions will have opposite signs. This means momentum can be changed by altering either the speed or the direction of the object. So, for example, if a ball bounces off a wall, there will be a change in momentum even if the speed is the same because the direction in which the object is moving has changed. So you can have a change in momentum either by altering the speed or by altering the direction. Now, unless stated in a question, you can assign the plus and minus with the direction. But please remember that if one direction is positive, its opposite direction is negative. So if up was positive, down would be negative. Now, this allowed Newton with his ideas in mathematics. So let's just clarify what we've learned. Isaac Newton defined momentum to be mass times by velocity. The unit of momentum is defined to be kilograms meters per second, and momentum is given the symbol of P, and it has to be a dynamic quantity. You need motion to have momentum. So here is our equation. Momentum is equal to mass times by velocity. It has both a magnitude and a direction because momentum is a vector. And if objects are moving in opposite directions, they have opposite momentums. This is signified by one value being positive and the other value being negative. And if you're not given a clue in the question as to which one is positive and which one is negative, you can decide that for yourself. So that's very, very important to understand. Now, this allowed Newton to write his laws in terms of momentum. So now, Newton's first law, which what we say in the modern day is that objects stay at rest or move with a constant velocity unless acted upon by a resultant force, we can actually write that as a resultant force changes the momentum of an object. Newton's second law, that the resultant force is equal to inertial mass times by acceleration, well, we can also say that the resultant force is proportional to the change in momentum every second. And finally, Newton's third law, which we know is that when two objects interact, they exert equal but opposite forces of the same type on each other. Well, we can write that as, for a system of objects, the total momentum of the system before equals the total momentum of the system after, as long as there's no external forces on the system. Now, when Newton wrote his laws in motion in 1687, he published his work in his famous book, the Principia Mathematica, which is Latin for the mathematical principles of natural philosophy, physics. Now, in this book, he wrote his laws of motion in terms of momentum, not in terms of forces. So it could be said that momentum is the true quantity Newton used to describe momentum. Now, interestingly enough, only 400 copies were made as the first edition of the Principia Mathematica, which were all signed by Isaac Newton. Now, a first edition value today is at about $3.7 million. And actually, Cambridge University Library has Newton's own copy of the first edition with his handwritten notes for the second edition, and is actually thought to probably be the most valuable book in the world, and it's on display at the Cambridge University Library. Now, Newton's third law is one of the most important laws in physics, and basically we can write that as momentum has to be conserved in any collision or any explosion. So what we are saying that is the total momentum before a collision or explosion must equal the total momentum after that collision or explosion. So that is from Newton's third law of motion. Now, that could be simplified by saying that the mass of the object times by the velocity of the object before the collision or explosion is equal to the mass of the object times by the velocity of the object after the explosion. Now, what can happen is momentum can change in between objects of the system, but the total momentum of all the objects remains fixed. So say, for example, you had two objects before a collision. One had a momentum of 5, the other had a momentum of 7. So as a result, you had a total momentum of 12. Well, after the collision, one object could have a momentum of 2 and the other could have a momentum of 10. So whilst for the individual objects the momentum has changed, the total momentum before and after has remained the same. Okay, 12 before and 12 after. Now we call this idea the conservation of momentum. Now, we'll cover this more in upcoming lessons, but conservation means to keep the same. So if the total momentum is the same as the total momentum after a collision, you have a conservation of momentum. Now, let's just have a look at this idea in the real world, because it governs the mechanics of all collisions and explosions in the universe. So, for example, looking at these various situations, they're all governed by the conservation of momentum. In all these situations, momentum was the same before the collision or explosion as it was after the collision or explosion. But let's look at a couple of examples of how you calculate the momentum of any object when it's in motion. So, for example, Valtteri Bottas is driving in the French Grand Prix. The total mass of Bottas and the car is 710 kilograms. He's traveling at a velocity of 120 meters per second. What is his momentum? Well, the first thing you would do is you'd write out the equation for momentum. Momentum equals mass times by velocity. You then plug in the values. Remember, it's always extremely important to sub in the values into your equation before you think of rearranging. In this case, you'll have to rearrange, but always try and do that. You then multiply the two numbers and you get an answer of 85,200 kilograms meters per second. Now, note again, we'll have the correct number of significant figures and the correct number of units in our values. Now, in each value so far, we've been given 3 sig figs, so we have our answer to 3 significant figures. And then finally, let's have another example. That Alan Saint Maxima is running with the football at a speed of 8.8 meters per second. He has a mass of 67 kilograms. What is momentum as he runs? Well, momentum is equal to mass times by velocity, so momentum equals 67 times by 8.8, so it's 589.6 kilogram meters per second, but we round to the correct significant figures, which is 590 kilogram meters per second. So we give our answer with the correct number of units and the correct number of significant figures. So what have we learned in today's lesson? Momentum is defined by the equation. Momentum equals mass times by velocity, with momentum P in kilogram meters per second, mass M in kilograms, and velocity V in meters per second. You should be able to apply and recall this particular equation for your examination. So if you've been successful and learned in this lesson, you should be able to define what the quantity momentum is, calculate momentum information, and apply this information to understand how momentum can be used accurately and reliably in different contexts. I hope you've enjoyed today's lesson on momentum and have a lovely day.